All right, so the very first problem that I want to do is the following. So some of you probably seen examples like this already, but if not, uh, that's why we're here. Let's say if we have the integral of ln of t minus 7 over t minus 7 dt. To compute this integral, this indefinite integral, we have to make a u substitution. What do you think would be my u? Say it louder. That's right. You have to actually make the entire ln expression, ln of t minus 7, be your u. So in this example, we let u be equal to ln of t minus 7, and then you find your derivative du. So if u is ln of t minus 7, your du is going to be the derivative of t minus 7. So what is the derivative of t minus 7? 1, right? Because the derivative of t is 1, derivative of negative 7 is 0, divided by t minus 7. So you have 1 over t minus 7 dt. Okay, now inside of your integral, do you have a 1 over t minus 7 times dt? Yes, right? You could have rewrote this particular integral, the original integral, as ln of t minus 7 times 1 over t minus 7 dt. So therefore, you can now recognize what's my u, what's my du. We have that u is going to replace the entire ln of t minus 7, and du replaces the expression 1 over t minus 7 dt. And this is something now that's much easier to integrate. You could use the power rule for integration. What is the antiderivative of u? U squared over 2. And what are you missing? Plus c, because we're dealing with an indefinite integral, so don't forget the plus c. All right, and now what we can do is just make a replacement. We define u as ln of t minus 7, so we get ln squared of t minus 7 over 2 plus c. You could have write the square on the outside, but I like to square, in this particular problem, the ln, because if I put the square on the outside, then it appears that it could be misleading. You would think that the t minus 7 is being squared rather than the ln expression. So to avoid that ambiguity, sorry about that, just square the ln rather than putting it on the outside of t minus 7. Are we all good on this first problem? This is just warm-ups, okay. Let's look at part B now. Let's say in part B, we have the integral of negative 5 e to the x over 17 e to the x plus 3 dx. In this integral that I have, you can also solve this by making a u substitution. Before I make a u substitution, however, let's just do a quick rewrite. If you look at the numerator states negative 5 times e to the x. So these constant multiples, like negative 5, for example, you can pull it outside of the integral. Now, you're probably wondering, can I pull the 17 out as well from the denominator of 17 e to the x plus 3? The answer is no. You can't pull the 17 out, but you can pull the negative 5. Because in the denominator, it's reading as a binomial expression, 17 e to the x plus 3. So the only way for me to pull out, let's say, a 17 is if instead of having a plus 3, we had a multiple of 17, such as itself, 17, 34, 51. It had been a multiple of 17. But because the binomial expression is prime, the only GCF there is 1, you can't pull a 17 out essentially. If it was a product, by the way, if it was 17 times 3 times e to the x, then you could have pulled out all those constants, 3 and 17. Okay? All right, so just pulling out this negative 5 makes our integral a little easier to work with. We have e to the x on top, all divided by 17 e to the x plus 3 dx. Okay, now what we can do here is use a u sub. what would be my u in this example? The denominator. The denominator is going to be my u. Why is that? The reason for it is, well, let's just say I made u be e to the x, right? If I did u equals e to the x, what is the derivative of e to the x? E to the x, right? So you got du is equal to e to the x dx. But if you look at inside of the denominator here, your denominator reads as 17 e to the x plus 3. Your du will need to essentially replace that entire expression. But our current du here cannot. So therefore, u cannot be e to the x. Well, that leaves us with making u be equal to the denominator. 17 e to the x plus 3. You get your derivative, du. So what is your derivative of 17 e to the x? 17 e to the x, derivative of 3. The derivative of 3 is 0, and then you attach the dx at the end. Now, if you look at your du, it's 17 e to the x dx, right? However, in the numerator of our current integral, it's e to the x times dx. So for our du expression, you just got to do one more rewrite. Divide by 17. Now, instead of dividing by 17, you can say that you're multiplying by the reciprocal of 17. What is the reciprocal of 17? 1 over 17, right? So I could just rewrite my particular du here as 1 over 17 du equals e to the x dx. Now, the 1 over 17, do I need to have it inside of the integral? No, not at all. You can pull it out. So because we have the -5 on the outside already, we're going to have -5 times 1 over 17. The integral of, well, du is now replacing the e to the x over dx times dx. And we're dividing this by u. Okay, now we're going to get -5 times 17, which is -5 over 17. The integral of, you could have rewrote du over u as u to the -1 du, right? By just simply bringing u up into the numerator. And then try to integrate this. Unfortunately, if I use the power rule here, the power rule cannot work. So what rule do I use here? Not the chain. Say it louder. Say it louder. ln, yes. You use the ln rule. So because the power of u is -1, we can't use the power rule because when I add 1 to -1, what does that equal to? 0. Can you divide by 0? No, right? So therefore, by the ln rule, you'll have -5 over 17 times ln of the absolute value of u plus c. And since u was defined as 17 e to the x plus 3, you just make your replacement. So we get -5 over 17 ln of 17 e to the x plus 3 plus c. And that would be your final answer. Any questions with the second example here? Maha, if you have any questions, just remember, just let me know in the chat. It's on our website, by the way. They can go to Math Student Success Center. They could literally just Google it, and then you scroll down on our webpage, and the Zoom link is there. Oh, sorry about that. Can you just copy that link and just send a screenshot to the group chat to let them know? All right. Can I continue? Alrighty. So that's example number 2. Let's look at example number 3. Again, the whole point of this problem is just to go over different ways of finding answer to find indefinite intervals. Go over different techniques. So this first example, problem one, is going to be lengthy. All right, let's look at part C. Let's say if I have the integral now of x e to the negative 4x dx. For this particular integral, what method do you think I'm going to use here? For example, do you think a u substitution will work? No, it's not. So what other technique? By parts. Very good. You use integration by parts. So for part C now, we're applying integration by parts. So I'm going to abbreviate it, integration by parts. And the formula for it states that if you have the integral of, I believe we say u times dv, then this is equal to u times v minus the integral of v du. Okay? So what would be my u here? Yeah? No, I don't think a u sub could work here. U substitution won't work. Look, if you make u equals to negative 4x, what is your derivative? Wait, look, pay attention. Look, I'm explaining it. If u is equal to negative 4x, what's my du? What's my derivative? If u is negative 4x, what's our derivative? Negative 4. Du is equal to negative 4. Now, inside of my integral, do I have a negative 4? No. And in particular, we have an x. So that means that if I made u equals to negative 4x, then the du cannot replace that x. So therefore, this can't work. All right, so for this example, we're using integration by parts. Now, the good thing about when you're applying integration by parts in this particular example here, your variable x is usually, or majority of the time, is going to be your u. Your dv is going to be the e to the negative 4x dx, okay? So we make u equals to x, and we have dv is going to equal, that's a v by the way, dv is going to equal to e to the negative 4x. That's a negative 4. Yep, e to the negative 4x dx. Okay, now what is the derivative of u? 1. So we say du is equal to 1 dx, or just simply dx. Now for dv, we have to find the antiderivative. Now, what is the antiderivative of e to the x? E to the x. Now, the thing about it here is that your exponent, the variable x is being multiplied by negative 4. So you see, essentially, we're using a u sub there informally. But the shortcut to it is that whatever is the coefficient of x, you just divide by that coefficient. So my coefficient of the x is what? Negative 4, so we divide by negative 4. So our v is simply going to be e to the negative 4x divided by negative 4. Or you could clean this up a little bit. You can say that this is negative, just pull the negative sign outside of the fraction, and you will have negative e to the 4x, or negative 4x, all divided by 4. All right, you apply your integration by parts now. By integration by parts, you take u times v. Right, so this integral is going to give you u times v, which is x times negative e raised to the power of negative 4x, where all of that gets divided by 4, minus the integral of v times e du, v times du. So we'll have negative 4, or negative e raised to the power of negative 4x divided by 4 dx. Now you could clean up your equation per se, right? You could clean this up a little bit. You could take x and multiply it by e, so you can write that out as one fraction. You have x times e to the power of negative 4x, all divided by 4. Now, for the integral part, you can pull out the fraction of 1/4. Or, namely, you can pull out the fraction of negative 1/4. But just be careful. If I pull a negative 1/4 out of my integral, because I have a negative sign already on the outside, what happens to my two negatives? It becomes positive. So this becomes plus the integral, plus 1/4, the integral of e to the negative 4x dx. Now, for this new integral, or the simplified integral here, do I need to use integration by parts again? No, we don't need to use integration by parts because we already know what's the antiderivative of e to the negative 4x. The antiderivative of e to the negative 4x is simply negative e raised to the power of negative 4x, all divided by 4. So our next line that we should write is, okay, we bring this down, negative x e negative 4x over 4 plus 1/4 times negative e raised to the power of negative 4x, all divided by 4 plus c. You can clean up your answer just slightly here. You could take 1/4 and multiply it by negative 1/4. That'll give you negative 1/16. All right, so I'm just bringing down the first line again, or the first expression. So you'll have minus e to the power of negative 4x over 16 plus c. And that will be my final answer. There's other ways of rewriting your final answer for this example, but this will suffice. Any questions? All good? All right, let's look at another problem where we use, I'll give you a hint, we're going to use integration by parts. Is it okay if I slide this down? All right, I'll leave half of the example up. I'll just change the color. So let's say in part D, I have the integral of x to the third times ln of x dx. What do you think will be my u? There you go. You see now, if you have an integral in the form of x to the n power times ln of x, you make your ln of x be the u and make the dv be your x to the third power in this case, okay? So u is equal to ln of x, dv must be x to the third dx. Okay, now, what is the derivative of ln of x? 1/x. Derivative of ln of x is 1/x, so we say du is 1/x dx. And what is the antiderivative of x to the third? X to the fourth over 4. Okay, so by integration by parts, our current integral now is equal to u times v. So that's ln of x being multiplied by x to the fourth over 4 minus the integral of v times du. So we have x to the fourth over 4 multiplied by 1/x dx. All right, let me just clean this up a little bit, and then we'll try to get the final answer. So ln of x times x to the fourth over 4, I can write it as a single fraction. We can say that's equal to x to the fourth times ln of x, all divided by 4, minus, now inside of this integral, I can simplify it a little bit. First of all, I could pull out a constant multiple. What is the constant multiple that I can pull out here? Say it louder. 1/4. You can pull out the 1/4. And then you have the integral of x to the fourth over x. But what is x to the fourth over x? Can you simplify that? X to the third. Right, so just cleaning up the integral part here, you get negative 1/4 of the integral x to the third dx. Now, let me ask you this question. Did we find the antiderivative of x to the third before? Yes or no? Yeah. So the integral of x cubed is x to the fourth over 4. So I just got one more line to write. We say we have x to the fourth ln of x over 4 minus 1/4 of x to the fourth over 4 plus c. You can clean this up a little bit. So just rewriting the first term, the first expression. 1/4 of x to the fourth over 4 is now minus x to the fourth over 16 plus c. And that will be your final answer. Somebody had a question. You can ask your question now. Because it's by the integration by parts, you're doing v times du. So you're multiplying x to the fourth over 4 by 1 over x dx. Yes. Integration by parts, right? The formula states that if you have u dv, it's equal to u times v minus the integral of v times du. Okay? Somebody else have a question? Somebody said, how did I get? Okay, wait 1 second. Did you write out the formula, ma'am? Good? All right.
Excuse me.
How did I get what? First line. Oh, because what I did was I pulled out the constant multiple, right? Think about it. That expression, x to the fourth times 1, is being divided by 4 times x, which is 4x, right? So you have, if you were to actually multiply this out, it's x to the fourth all divided by 4x. So the constant multiple, which is 1/4, can be pulled out. You could rewrite this as 1 over 4 times x to the fourth over x. So the 1/4 goes outside of the integral. X to the fourth over x is just really x cubed. Now, somebody had a question. Also, I heard somebody in the Zoom meeting. What I ask that you kindly do is type your message in the chat, only because if you speak in the Zoom meeting, it echoes. And anybody else?
I just typed it.
Oh, hi, Carlos. So you asked why is dv, for the previous example. So the previous example, essentially the shortcut of it is that your antiderivative is going to be e to the negative 4x, but instead of, if you think about the chain rule for derivatives says that you would have multiplied by -4. Well, the chain rule for, or u substitution essentially for integration says that you're no longer multiplying, but you would rather divide by -4. Okay? All right. Anybody else? All right. I'm going to put up 3 examples now. These 3 examples, they all look almost the same, except no, Carlos, that cannot be applied. That's the chain rule for derivatives. You have to use the chain rule for integration, which is u sub. Yeah. Wait, you lost me. The third line here? Here? Uh-huh. Well, it just so happens, but I mean, it depends. Yeah, well, it depends on the examples you choose. Yeah? Yeah, go ahead. That's the same thing. It doesn't matter. It's just more formality just to put the variable term, like x to the fourth in front, like x to the n power. You usually put it in front of your natural logs, your e to the x, your exponentials, or even your trig functions like sine, cosine. It doesn't matter. A times B is still B times A. All right, let me get to these next couple of examples. Carlos, I won't be able to answer that question at the moment because if I do, then I won't be able to get through these particular examples, and it's important that I do. I'm sorry. So again, I have a few more examples I want to show you. There's an E, there's an F, and there's a G. So I'll do it all separately, but I want to show you these three examples. The first one is 4 over x squared plus 9 dx. The second one is 4x over x squared plus 9 dx. And the third one is now going to be 4x cubed over x squared plus 9 dx. Now, these examples, they all look similar because it contains the x squared plus 9 in the denominator. It contains a 4 in the numerator. But if you look at parts F and G, you have x and then follow it with x raised to a power. So there are different techniques used to actually find their antiderivatives. First of all, if I want to solve part E, if I want to solve this first example, one of the more easier way to recognize what technique to use here is you can pull the constant multiple out, right? You can always do that. The constant multiple that I can pull out here is 4. So when I pull the 4 out, this becomes the integral of 1 over x squared plus 9 dx. Now, there's a rule that you can use here to get this integral. And what do you think that rule is going to be? I'll give you a hint. U substitution is out of the question. Yeah? There you go. You have to use the tangent rule, right? So for this first example that I'm showing you here, this piece, this integral resembles, right? So this is just a little note here. It resembles, sorry, I spelled resembles wrong. It resembles the integral of du over a squared plus u squared. Now, a squared plus u squared is the same thing as u squared plus a squared. That's fine. So in this problem, what do you think is my u or my u squared? Yeah, so in this problem, we have that u squared is equal to x squared. Now, if u squared is equal to x squared, then what would be my u? Well, sorry, if u squared is equal to x squared and I take the square root on both sides, then u is equal to? No, where are you guys getting these numbers from? Not square root of x, just x, right? U squared is equal to x squared. So if you take the square root on both sides, the square root of u squared is u. The square root of x squared is x. Okay, good. Well, I'm showing it to you, okay? So if you have a squared is equal to 9, then a is equal to what value? 3. Now a is equal to 3, okay? So what the tan rule says or states is that if you have the integral of du over a squared plus u squared, then this is equal to 1 over a times arctangent of u over a plus c. Okay? So in my next line, I can write it as follows. Looking back at the original integral, we had a 4 that was on the outside, so the 4 is going to be part of the solution. So I say 4. Now, in the brackets, I'm going to use the arctan rule. For the arctan rule, you do 1 over a. What's the value of a? 3. So you get 1 over 3 arctan of u over a. What's my u? X. What's my a? My a is 3. And then you say plus c at the end, okay? So if you want to clean this up, you could have did 4 times 1/3, which is just simply 4/3 of arctan of x over 3 plus c. And that would be the solution for part E. Okay. So the idea into part E was just to recognize that the denominator was a sum because we're adding, a sum of two squares. Anytime you see that the denominator is a sum of two squares, then you know that essentially one way of integrating could possibly be the arctan rule. The arctan rule will be applied as long as the numerator is a constant. Okay? Question. So what? I think that's okay. But if you're doing this, like, let's say on my lab, they probably want you to simplify it a little further. Sorry, I just couldn't hear you because the air conditioner. Gotta speak louder in the room. Not in this example, Maha. No, you cannot. Because again, if you make, again, this is why I said it at the beginning that U substitution is not going to work, and you have to think about why it's not going to work. I'll do it again. If U is equal to x squared plus 9, what is the derivative of U? You get 2x. There you go. So du is equal to 2x dx. Now, inside of the integral here, do you have, forget about the 2, do you have an x inside of this integral in the numerator for part E? No. So U substitution couldn't work. It couldn't work. Where's the what? Oh, the du comes from taking the derivative of U. So in short, the derivative of U with respect to x is du over dx. But you rewrite it as just simply du equals the derivative times dx. Okay, so yes, U substitution doesn't work in part E. Let's actually look at part F now, because part F is a little interesting. So I'm going to rewrite part F for us. Part F, you have the integral of 4x all divided by x squared plus 9 dx. All right, what do you think we're going to do here? First of all, okay, Paulo, sure. In this example, for part F, what would be my, what rule do you think I could use here? For example, do you think the arctan rule can be applied here? No, it cannot be applied because the numerator now contains a variable term, namely the x. So arctan can't be applied. What other rule do you think can I use? Use a U substitution. Now the U substitution actually works in this example. Why? Well, first of all, you could have pulled this constant out, right? Like I showed in the previous example. You could have said that you had 4, the integral of x dx, all divided by x squared plus 9. So in this example, make your U be the denominator, x squared plus 9. Now, your du is equal to 2x dx, because we already showed it. But inside of the integral, our second integral, it's x dx. Our du is 2x dx. So what do you think I have to do to that du, that equation? Multiply it by 1/2, right? So if I multiply it by 1/2, you get 1/2 of du equals 1/2 of 2 times x dx. So the 1/2 and 2 would cancel out. You get x dx here, okay? So you rewrite this integral now in terms of your u. Now the 1/2 can go on the outside, so we have 4 times 1/2 of the integral of du replaces x dx, and u's on the bottom, which is x squared plus 9. All right, now what's 4 times 1/2? 2. So this will give us 2 times the integral of du over u. But you should recognize this example now. We did this one before. What rule is being applied? The ln rule. So you get 2 times the ln of u plus c. But what's my u in this example? X squared plus 9. So you get 2 times ln of x squared plus 9 plus c. All right, so that's the example in part F. Any questions on it? Yeah? Divide 2 on both sides, it's like the same thing as saying you're multiplying 1/2. The ln du over u, rewrite it as u to the negative 1. Yes. I did an example earlier, that's why I didn't do the other rewrite. Anybody else? All right, let me show you part G. So for part G, let's say that example was the integral of 4x to the third over x squared plus 9 dx. Now let me ask you a question. Do you think u substitution is going to work? Yes or no? Do you think, great, gotta pay attention. Do you think u substitution is going to work here? No. One of the reasons why u substitution is not going to work is look at the degree of the numerator and compare the degree of your denominator. What is the degree of your numerator? 3. The degree of your denominator? 2. You see, any time that the degree of the numerator is equal, greater than or equal to the degree of the denominator, you have to, one way of computing this integral is first doing long division. Right? So if the degree of n, meaning n standing for the numerator, is greater or equal to the degree of the denominator, then apply long division. So you should have seen long division in pre-calculus, which was probably a year ago, a year and a half ago. So we're going to review the long division here and to just simplify this expression, okay? So aside, for long division, here's your long division bar. Inside of it, you put the numerator, which is 4x cubed, and in your denominator, your denominator goes on the outside, directly to the left. So that's x squared plus 9. Now, one thing to also note is that if you compare the numerator, 4x cubed, to the denominator, x squared plus 9, notice that notice that the numerator contains powers, doesn't contain powers of the denominator. So you can use fillers. Like, for example, because it doesn't have an x squared term, you can say plus 0x squared. All right? If you wanted to, you could have did this for plus 0x plus 0. You could have added how many more zeros you wanted, so that way, when you apply your long division, you're not missing any descending powers when it goes down by 1. Okay. All right. So here's how you do the long division. First, you want to ask yourself, how many times can x squared go into 4x cubed? Right? Mathematically, it looks like this. Simplify 4x to the third over x squared. If you simplify this, what do you get? You get 4x. So you take the 4x, you can write it now above the, where it says the 0x, you can write it above, so it can line up accordingly, the powers. And now you can take 4x and multiply it by x squared plus 9. What is 4x times x squared? 4x to the third. Now, what is 4x times 9? Say louder. 36x. So the 36x, do you think I'm going to write it above, underneath the 0x squared or the 0x? Write it underneath the 0x. Very good. So here you would have had the 36x, and in between, I could have just put 0x squared, so that way everything just flows nicely. All right, now I'm going to do the subtraction. What happens when I take 4x cubed and divide it by, 4x cubed and I subtract it from itself? It's 0, it cancels out. If I take 0x squared and subtract it from itself, what happens? It's 0, right? That's also gone. Now 0x minus 36x would be very good. You get negative 36x. Now here's my question, right? Now it's just a matter of repeating it, but be careful. Can x squared go inside of negative 36x? No, it cannot. So therefore, negative 36x, we call that the remainder. Very good. So this will be your remainder. So what I showed you in this example is that 4x to the third over x squared plus 9 can be rewritten as 4x minus 36x over x squared plus 9. And this now becomes a little easier to integrate, okay? So the original integral was 4x cubed over x squared plus 9 dx. By long division, we have now the integral of 4x minus 36x over x squared plus 9 dx. And again, if you wanted to, you could split this into two integrals. You could have said that you have the integral of 4x dx minus 36, the integral of x over x squared plus 9 dx. So just a little disclaimer here, just please pay attention. The negative 36x, I could pull the negative 36 outside of that integral technically, of the second integral. And inside of the second integral, you'll get the x over x squared plus 9. Okay? All right, now we can integrate all of this good stuff. For example, what is the antiderivative of 4x? Say it again. 4x squared over 2. So don't worry, I'll simplify it at the end. So this piece is going to be 4x squared over 2. Now, for the second integral, we'll get minus 36. Well, what do you think I need to do here for that second integral? Say it louder. You make a u sub. What will be my u here? Let u be equal to x squared plus 9. Du is going to equal to what? Two x dx. Now, do you have a 2x dx inside of the original, inside of that integral there? No, it's x dx, so you multiply by 1/2 or divide by 2, whatever you like. So I multiply by 1/2. I say 1/2 of du x dx. So what we're going to have is 36, negative 36 times 1/2 of the integral. So I have to do a u sub there. I had no other choice. 1/2 of du over u. But again, if you see du over u, what rule am I applying? ln. Very good. So we have 4x squared over 2. We can simply clean that up a little bit. That's just 2x squared. Negative 36 times 1/2 is just negative 18. So it's negative 18 of ln of u plus c. But the u was my x squared plus 9. So it's 2x squared minus 18 ln of x squared plus 9 plus c. This is a very good exam problem to put. Sorry. Maybe you're gonna learn it soon when you do partial. Have you did partials yet? Nope. Have you guys did partials? Excuse me. Have you did partials? You did? I'll do partials next week because I'm not prepared for partials yet. I gotta look back at some stuff. Yeah, question? Again, if you see du over u, it's ln of the absolute value of u. It's where the power rule does not apply. Okay. All right. Anybody else with a question? There's one more example I want to show you of computing indefinite integrals, and this one now I'll walk you through it. This example is called completing the square. So I don't know if if your professor's gonna show you this stuff before partials, so I'm gonna show it. I know it's on your exam. It's here on your exam, so I'm gonna show it.
We didn't have them this week, so that's why.
That's okay. Grab some popcorn and sit back and enjoy the show. All right, so let's look at part H, and then I'll stop the recording. So we have the integral. I don't know who class you're in, Maha. On the integral of 3 over x squared plus 6x plus 13 dx. Well, first of all, everyone, do you think U substitution is going to work here? No, it's not going to work. Let's try to clean up this integral a little bit. First thing is you can pull your constant multiple out. You can pull the 3 out. So this will give you 3 times the integral of dx all divided by x squared plus 6x plus 13. Now, essentially what you can do here with this integral is first, look at your denominator and apply completing the square, okay? The way that the completing the square is going to work with our denominator is as follows. I rewrite it as the following. I say that x squared plus 6x plus 13 is equal to, in parentheses, x squared plus 6x plus blank, close parentheses, plus 13. And then I'm going to say minus blank. So essentially what I'm doing here, right, I have an equation. So essentially what I'm doing is that I'm adding and subtracting by some number. The blank represents a number, and I'm adding and subtracting by that number. Now, it doesn't make a difference because when I add then subtract by that number, right? If I have 5 minus 5, what's 5 minus 5? 0. You get 0, which means that if you get 0, did I change anything with the original equation? No. I'm just reformatting the original equation so that I get a, I can apply my completing the square, essentially, okay? So the way that the completing the square works, the blank part, this value, is being filled by taking the value of b, of the trinomial, divided by 2, and then squaring it. So what is my value of b inside of the parentheses? Say it louder. That's 6x, but 6. It's just the coefficient of x. So this will be 6 divided by 2 squared. Now what's 6 divided by 2? 3. So this will give us 3 to the second power, which is 9. So this number will become plus 9 inside the parentheses, and then you have a minus 9 on the outside. Again, I'm dealing with an equation. I'm doing a rewrite, so I'm adding, subtracting by the same number. All right, we're almost done with the completing the square because we have x squared plus 6x plus 9 plus 13 minus 9. What's 13 minus 9? 4. Now look at inside of the parentheses. X squared plus 6x plus 9. What does that factorize? X plus 3 squared, right? Because what are 2 numbers that multiply that give you 9 that adds up to 6? Those 2 numbers must be 3 and 3. So you would have had x plus 3 times x plus 3. But if it's the same binomial being multiplied by each other, you write it as the binomial square. So it's x plus 3 raised to the second power plus 4. All right, so now that I have the completing the square completed for our integral now, going back to it, originally we had the 3 on the outside, dx on top, now divided by x plus 3 squared plus 4. The dx, sorry, it was already on the top. Okay, now look at the denominator. What do you think I'm going to use? Say it louder. You use the arctangent rule, right? If I want to apply my arctangent rule, what's my u squared? Say it again. X plus 3 squared. And then what's my a squared? 4. So u is just simply going to be x plus 3. A is equal to 2. So by the arctangent rule, what we're going to have is 3 times 1 over a, so it's 1/2 times arctan of u over a, so that's x plus 3, all divided by the value of a, which is 2, plus c. And then you could take the 3 and multiply it by 1/2. So this gives you 3/2 of arctan of x plus 3, all divided by 2, and then plus c at the end. And ta-da, that is your final answer.